Welcome back. This time, let's start off with a little bit of practice on implicit differentiation. Usually it takes a lot of practice, and then we'll see how we can use that to find the derivative of inverse functions. So, first things first, give this one a shot. Maybe pause the video, see how far you can get. There is a trick to making this one a bit faster. Okay, I'm going to go ahead and give it a shot. Looks like if I take the derivative of sine, I get cosine of y. But again, we treat y like a function, so we need to do the chain rule on it. We get its derivative. Again, people will write y prime here. I find that pretty confusing when you're dealing with exponents on y's, and also when you have other variables flying around. It's really nice to get in this habit of just writing dy dx. Okay, I've got to do the product rule over here. So I get a 1. I leave the y squared alone, plus I leave the x alone. I take the derivative of the y squared, 2y times dy dx. Very nice. Now, I want to show you the long way and the fast way to do this. The way we did this last time was to bring everything with the dy dx to one side, which will work. And then leaving everything without, or putting everything without a dy dx onto the other side. So it looks like I just have a y squared to leave over there. Then I factor out this dy dx. So this is a minus 2xy. Why do I do that? I do it so that I can then divide. So dy dx equals the right side divided by that factor on the left side. Ta-da! And so now if I wanted to, I could go ahead and plug in, say at 0, 1, and I plug into this thing, and I get 1 for my y value, cosine of 1. Cosine of 1 is not a nice number, minus, it looks like a 0. So I get 1 over cosine of 1. That's a pretty gross number. But who cares? Cosine of 1 is not so bad. Let's see the easier way, shall we? Hopefully that made sense, because you'll still need to do that. If, however, you know that you've got a point here that you're worried about, you can make your life easier right after you take that derivative. Right after you take the derivative, you are in good shape to save some work on the algebra. So instead, let's just plug in right away, rather than waiting till the end. So if I plug in, I get cosine of 1 dy dx minus 0 equals 1 squared, which is just 1. So by plugging in, I just simplified everything a lot right away. We already know the x and the y values. Let's go ahead and use them. And now I can really quickly solve this for dy dx equals 1 over cosine of 1 at 0, 1. So if you have the x and y values, feel free to just plug in right after you take the derivative. You cannot plug in before you take the derivative. If you do that, the equation looks like constants on both sides, and you just get 0 equals 0. That's no good. Okay, we get a prize for our hard work. We get to take the derivative of a new kind of function. In fact, any inverse function you can use this technique on, but especially inverse trig functions. Let's see why. So y equals sine inverse of x. There is a special way of writing this, which is that this is the same thing as sine of y equals x. That is actually the definition of an inverse, is that this should be true, right? That taking the inverse of one side is the same as taking the original function to the other. Sometimes it helps if I do a little side work and people say, okay, well, if I had y equals sine inverse of x, and I took sine of both sides, so if I took sine of both sides, then they see that those sine inverses cancel, which is what an inverse should do, is cancel. So that's true, and it does work that way, but maybe a bit more fundamentally, the definition of an inverse is that it should be the thing. It should be the thing that satisfies this relationship. But if you want to just go ahead and apply sine or whatever the original function is to both sides, that is another way to get there. So I have sine of y equals x, which would have looked terrible, but now we can actually do something about that. We can actually take the derivative to try to find it. So this just looks like cosine of y. So if I take the derivative, dy dx equals, the derivative of x is just a 1. And I solve this for dy dx is equal to 1 over cosine of y. Cool. That's pretty neat. 1 over cosine of y is true. However, we really would like to write this using x's instead of cosines. So let's go ahead and give that a try. Let's go ahead and plug back in y. There's a little trick here that's going to help us out. There's a couple of different ways we could do this. What I have is I want to replace this y with this sine inverse. Kind of like above, we're going to use that original function to plug back in to give us some insight. But I don't really want to think about cosine of sine inverse of x. We could use something called a reference triangle to figure that out. Instead, I'm going to do something a little tricky. Let's do a little more side work here. Sine squared plus cosine squared equals 1. So if I do the work here, cosine is equal to the square root of 1 minus sine squared from the Pythagorean identity. So go ahead and try to solve for cosine there if you've never tried that before. I'm going to rewrite this over here real quick as 1 over the square root of 1 minus sine squared of y. That might seem silly until you realize I have a sine inverse and I desperately want to write this cosine in terms of sines so that I can get them to cancel. And that's exactly what's going to happen right now. Let's get these to cancel. I'm going to replace that y with sine inverse of x. Now I have a sine squared of sine inverse of x. Remember that sine squared is just sine of whatever's inside all squared. So this becomes our final answer, 1 over the square root of 1 minus x squared because of that sine squared. That's it. That is our amazing derivative of sine inverse. This looks a little ugly at first. The process is really smart because it works for any inverse you want. You can try to make this same technique. This is amazing to me because we've got these things that live in trig world, and we take their derivative, and out comes something with square roots and squared and not a trig function in sight. Pretty incredible. In fact, I think there's a nicer one. Let's do this one as well because it's so nice and because the repetition is good. Let's go ahead and try tangent inverse. So I'm going to do the same thing as before. I'm going to rewrite this and say, tangent inverse of x. Rewrite this and say this is the same as tangent of y equals x. And now I can take its derivative using implicit differentiation. Derivative of tangent is secant squared. But now I have to do the chain rule because I'm taking a derivative of a y. And the derivative of x is still just 1. Just like before, let's go ahead and solve for dy dx. 1 over secant squared of y. All right, I've got some secant squares of y, but my y is secretly a tangent inverse. I need some kind of a relationship between tangents and secants. If only we knew some kind of relationship between tangents and secants. Maybe that looks similar to my sine squared over cosine squared. Oh yeah, we had something. It happens if I divide everything by cosine squared. This looks like tan squared plus 1 equals secant squared. Remember that secant is 1 over cosine. Nice. Follows right from the Pythagorean identity. So let's rewrite this one again here. This looks like 1 over 1 plus tangent squared of y. But y is equal to y is equal to tangent inverse. So this is just tangent squared of tan inverse of y. Ooh. So of x, right? Y is tangent inverse of x. Those cancel. I get a 1 over 1 plus x squared. Oh my goodness, how nice is that? All right, believe it or not, I would love it if now and forever you remembered. It turns out inverse tangent is the most important inverse trig function. It looks really nice. It is continuous on its whole domain. It has a nice asymptote at negative pi over 2 and positive pi over 2, and its derivative is 1 over 1 plus x squared, which is also always positive, defined everywhere, beautiful function. Great. Let's use these for a second here, just for some practice. Let's get some quick derivative practice. Tangent inverse of e to the x. Let's change colors so I don't run into the other parts. Tangent inverse of e to the x is going to be, well, this is just my chain rule in action, 1 over 1 plus e to the x squared, also known as e to the 2x, times my chain rule says take the derivative of that inner function, e to the x. This is just e to the x over 1 plus e to the 2x. Nice. Okay, as always, try these before you watch me do them, and if something happens that confuses you, pause it, see if you can do it on your own, and then see if it agrees. Okay, different kind of a chain rule problem. This is here to illustrate the differences between these kinds of exponents. This is not an exponent. This is an exponent. So I'm sorry about this notational issue, but to the negative 1 is restricted for inverses, whereas this 2 is an actual exponent, and that's how we need to write it. So a little bit of practice in visualizing that. I know it's confusing. Let's pull that 2 down because the chain rule says so. And now let's go ahead and take the derivative of sine inverse, see if we remember it. 1 over the square root of 1 minus x squared. That's it. Great. Little chain rule. Yep, there it is. 1 over 1 minus square root of 1 minus x squared. A little bit of practice to get those to stick in your head. If it's up to me, those are probably the only 2 I need you to remember. However, there are, of course, many inverse trig functions. By many, I mean 6. We already did 2 of them. Secant inverse looks similar, and you can get it a similar way. It turns out that it's not actually that hard once you get a couple to know the other 3, because they're just the negatives. This is one of these amazing things. So the derivative of inverse cosine is just negative 1 over the square root of 1 minus x squared. The derivative of cotangent inverse is just negative 1 over 1 plus x squared. And the derivative of cosecant inverse, I know I didn't prove secant inverse to you, but you should try it on your own. It's just the negative of x square root x squared minus 1. So nice. Different people have different opinions. I personally don't memorize all of these. I do certainly memorize inverse tangent. I try to memorize sine inverse, and then if you know the negative rule, then you're most of the way there. I usually have to look up secant inverse and cosecant inverse. They don't come up that much. Okay, that is it for this video. It was a lot. This section takes practice, but hopefully as you see it more and more, it gets better and better.